have sort of another part of my sort of like research in a sense is, so in a literal sense it's methods development, but I take that as quite a broad topic. I don't mean methods development as only algorithm development. I think there's a lot of great algorithms that get published that nobody uses because they're not practically very well supported for people to use them. And so we spent a lot of time in my sort of research career so far and in my plans for going forward, figuring out what it means to do practical and pragmatic methods development, which really comes down, a lot of it in my world, to coding well, right? And I can talk a little bit about that. Also, although I'm not that senior in this world, I'm sort of old enough to already have gone through 2 or 3 worlds of what it means to do technical research. When I was just starting, it was the era of machine learning. Through cognitive science, we've talked about all these things forever. When I was in grad school, data science was the term. This was before you were probably really aware of this, but 10 years ago, everything was data science. And we were at this big data science institute, and we talked to people hands-on Python programming for data science. And then that sort of shifted around. Now we're in whatever the world of AI means. That's a different world. It's still the same kind of machine learning, and it still could be called data science, but there's a lot of marketing terminology behind that. I don't really do that kind of work. We can talk about it a little bit if you'd like to. But yeah, I'm very happy to talk about like the literal, what does it look like to do this kind of work? The slightly maybe boring answer is it means sitting at a computer and writing code, which is what my job is. Anyway, okay. So I'm gonna sort of go through how I sort of think about situating my research. And this is how I start some of my research talks, which is to say that, we often have a research talk where we talk about, especially coming from cognitive neuroscience as my main home, where somebody will be like, I'm gonna tell you about memory. And they tell you things that they think might be going on in memory through behavioral data or modeling work and or neuroscience data, but they don't necessarily do a lot of details of how they got to these conclusions in terms of like the detailed analyses processes. And that is where I live. I live in sitting and thinking about those analyses processes because I think we sometimes underestimate their impacts and influences on the conclusions that we make, right? So if you do cognitive neuroscience or clinical neuroscience, not all of it, but much of it is going to follow something like this, where there is a brain that is, oh, that's useful. Okay, never mind. There is a brain that is of interest, or maybe a group of brains. I work with human neuroscience. This, it's conceptually similar if you're working with an animal model. And we record something, and then before we get to the answer of what we care about, we do a whole series of data transforms, right? And if you've worked in a lab in any means, you've sort of experienced this, that the notion like, oh, I can sit down, record EEG, and then know something about what the brain does in relation to memory, for example. There's actually a lot of steps between there. And that was sort of my first foray into this research, is being a cognitive scientist, cognitive neuroscience undergrad student, going to the MEG lab, so for our purposes, equivalent to EEG, and then being like, this is great. We can record electrical data in real time from the surface of the brain while they do language tasks, memory tasks, perception tasks. Cool. We must be like, day-to-day just solving questions about the brain, and then realizing that there's this whole sort of pipeline in the middle, and there's all sorts of complicated questions about what we do there, right? And so we have a series of steps that include transforming the data and then feature extraction. And feature extraction means the things that we talk about in terms of some brain phenomena that relates to our cognitive phenomena or clinical phenomena isn't something we recorded in a literal sense. It's something we sort of extrapolated and extracted. But we made a series of decisions to get there, right? And to sort of like cash out a little bit more specifically, most traditionally in EEG work, you will have heard of ERPs, event-related potentials. Does everybody know what that is? Somebody want to tell me what an ERP is?
It's like the electrical signal that's associated with, a task or like an activation.
Yeah, so if something happens, I flash a light, and I happen to be recording something for the brain, there's often an event-related potential, just meaning an electrical charge, so an event-related thing that happens in the recorded data. Neural oscillations, what's a neural oscillation?
Neuron go burr and activity increases and decreases.
Neuron go burr and activity. I mean,
Maybe the interesting way.
Yeah. Not no, but not all the way there. I mean, there's a couple nuances. This recording, if we're talking about EEG, is not neurons, right? It is the local field potential. We can talk a little bit about that, but approximately true. Oscillations, by description, means it's rhythmic. So there's lots of kinds of patterns that a neural activity can have. In fact, that's going to be sort of the whole theme of my talk. There's lots of kinds of patterns they can have. If you want to call it oscillatory, meaning rhythmic, meaning repeatable, you should be able to demonstrate some rhythmic, repeatable features of that kind of feature extraction. And if it doesn't have those features, we might be in trouble, which is a little bit of a foreshadowing. So yeah, anyway, sharp wave ripples, Daria might have talked about these or not, but they're basically just like a thing that happens in the brain sometimes. And I'm going to sort of talk about aperiodic activity. You might have heard less about this because it's traditionally been less studied, but a lot of my work has been saying, hey, there's this whole other class of features that we might sort of want to care about here, and what if we sort of thought about that, right? So we have this sort of data process, and then in cogneuro or clinical neuroscience, we try to take these features and relate them to some sort of cognitive or clinical measure of interest to interrogate their putative functional roles, right? So again, I'm talking about the kind of research where our goal is to understand something about brain function. That's not all research. There's lots of research in, for example, brain-computer interfaces, some areas of neuroengineering, that this isn't really the goal. The goal is to do decoding for a particular use case, and that's fine. That's a totally different kind of research, and it's not really what I'm talking about. I would argue in most of the time it's still better in that world to have better feature extraction, but it's not actually always necessary, depending what you're doing, right? But I live in the world where we actually want to understand something about cognitive neuroscience. And to try to like complete the loop, I do also have some work with collaborators where we try to connect to like system theoretical or computational neuroscience, right? So there's a whole world of modeling where we actually sort of build some sort of like computational system to interrogate how this kind of structures might sort of work, right? So the empirical angle and the theoretical angle hopefully are working together, right? Now, my sort of pitch here is that for this to work, we need to have robust and well-defined measures that actually extract something physiologically interesting and useful for us. There's lots of numbers, features, whatever we could take out of the system, and it's not necessarily the case that any sort of arbitrarily chosen feature is a physiologically sort of relevant way to talk about the brain, right? And if this goes wrong, everything else goes wrong. Again, in terms of understanding what is happening. You might be able to predict something relevant, but you might be sort of wrong about why you're predicting that thing if your feature is ill-posed or not very well defined, right? And so that is the motivation for my research program, which is developing methods for extracting robust and physiologically motivated features from neural fields data. If I use the word neural field data, it just means any electrical recording, EEG, MEG, intracranial, or animal model. We sometimes call it a local field potential. Any of those. So we want these features to productively allow for investigating cognition and disease in ways that can be interpreted or putatively interpreted in terms of underlying physiology. The feature itself can't necessarily be directly interpreted, I mean in combination with modeling and theoretical work, right? So that's the basic premise, right? Does this make sense as a sort of like, again, we often sort of talk about the end stage of this and the connection point. That's where I started too, coming through this research world, but realizing actually there's so much stuff that we do here that's, I think, often under-discussed, and it really has some jeopardy if we don't get it right. The other thing I'll add, which is sort of maybe latent, but I can try to say it more explicitly, like neuroscience in many ways is a young science without sort of a super clear, overarching, well-posed theoretical understanding in any general sense, right? If any of you've done any sort of like philosophy of science, we can talk about like maturity of science. So I'm not trying to get distracted there, but like, I do think neuroscience is the kind of science where seemingly basic assumptions can turn out to be sort of wrong. And if you think about even the very basics of neuroscience, the cellular principle that we have disconnected neurons, right? Like that was the Nobel Prize in 43 or something, right? These basic ideas are not that old. Hebbian plasticity comes from the 50s and the 60s, and we still aren't quite sure if it works like that was stated, right? Like you actually live in a world in neuroscience where basic principles are still up for testing. and can sometimes be reasonably wrong or totally wrong. And that I think matters for neurotechnology, right? Because you're trying to build technology on top of a sometimes shaky basis. Okay, so this is sort of my research program, but this I talked to you pretty abstractly. So I'm going to try to cash it out a little bit in what this looks like for these kind of signals. A little bit of sort of signal processing here. If you get unclear, again, throw up a hand, ask a question, let's talk about it. So how do we actually go about extracting features from neurophysiological recordings? I'm going to introduce the Fourier transform. Who knows what the Fourier transform is? Cool. Somebody want to tell me?
It breaks down a arbitrary signal into its frequency components.
Exactly. And that's I really like that you added arbitrary signals. So a Fourier transform is a bit of mathematical wizardry. It's used all over the place. Not all, like it's used in places where you might not realize is actually the core sort of foundational principle of a piece of data analysis. When I had that outline before of like raw data to data transforms, Fourier transforms are a transform. You go from one representation of the data to another. Time series representation means if this black trace is a hypothetical EEG signal, I put an electrode somewhere on your head. And over time, I recorded voltage. This just means I recorded some electricity, and it has some variation, right? What we typically like to do is understand what this is and what features it has. We could do that in the time domain. People do. I think that's great. That's not what I'm talking about. Oftentimes, you go to the frequency domain, which, as was pointed out, the Fourier transform is a mathematically perfect way to go from a representation in the time domain and represent that information in the frequency domain, meaning there's no information loss. It represents the same sort of signal in the world, but it has some quirks. Now, it does so with a set of sinusoids. What's a sinusoid?
It's a wavy line.
It's a wavy line, right? Sine wave in the sense that you know it from like whatever math in, I mean, I didn't do education here, so like high school probably. Trigonometry, yeah. Sine wave in the basics, like there's no trick here. It's a sine wave, it's a repeating rhythmic principle. Fourier transform is you can think of it sort of like a data decomposition or a data redescription, where we can take this black line, add a series of sinusoids. Each of these colored lines is a sinusoid that has a phase value, just where it is along its curve, and a power value, just how much of it is. And I can perfectly represent this black line by adding an arbitrary number of sine waves, and the red line reconstructs this. Does this make sense?
That's a very cool visual.
It's really good at
Yes, this became the sort of crux of my PhD. So at some point I was like, I just need to tell people what FFTs are in a very literal sense without a formula, because that's not really relevant. And so I spent a day making this, and that was probably the most useful day of the PhD. So yes, the point being that mathematically there's no issue here. I'm not talking to the mathematicians, they're doing great work, we love it. But psychologists, cognitive neuroscientists aren't always taking those outputs in the most sort of like technically careful way, right? Now the issue is, as maybe you can sort of anticipate, is just because you can create a representation of this black line with a set of sine waves doesn't mean that that representation is a good interpretation. What I mean by that is here actually what I've done in the black line is I have simulated one rhythmic component. So there is one big 10 hertz oscillation, which you can sort of see, right? But the rest of the variance in the black line is not rhythmic. It is, for our purposes, white noise. Do we know what white noise is? What is white noise?
background.
Yeah, it's basically white noise. Again, that's not a trick question. It's like if you hear audio white noise, it's the same thing. By definition, white noise is just sort of like random, meaning there is no rhythmicity to it. So white noise in the power spectrum has no frequencies, preferred frequencies, right? And so that's sort of the crux of this. White noise can be represented by an FFT as a sum of sinusoids, but it doesn't mean that that sum of sinusoids describes any rhythmic character. It's because sinusoids are so powerful, they can describe non-rhythmic events. Does that sort of make sense? So what does this look like if we sort of cache this out a little bit closer to neuroscience? So if I take the same kind of simulation from a hypothetical brain, I've just simulated this time series. Now this is what we're going to call the power spectrum. Is basically what we were doing in that slide before. I've ignored phase information because we almost always do ignore phase information. We can talk about that if you want, but for our purposes, it's just not really around right now. And we can have an ongoing recording, and we can have sort of a set of power values where this, maybe I should label this, these are frequency values. So 1 hertz, 2 hertz, 3 hertz, 10 hertz, 20 hertz. So how often per second that sinusoid oscillates. And this is power values, right? So just how much power is there in that sort of system. Now, what I'm showing you here is what I'm going to call a traditional model of EEG data analysis. Who's heard of theta waves? Alpha waves, beta waves. Do we know what these mean?
Related to the frequency?
Yeah, they're exactly what I've colored here, and I put Greek signals here. Theta, for example, is often something like 4 to 8 hertz. And so in a sort of operational definition, we sometimes can say that theta wave activity is the amount of power in 4 to 8 hertz. Now, maybe you're starting to see the problem here. That can be true in a descriptive sense, but does that mean that there's rhythmic activity in that band?
Is it that it's close enough, it's such a low frequency that it's close enough to like a DC level? Or like it's close enough to a non-oscillatory level? Like it might be representing the baseline.
Yeah, it's basically like what the baseline, right? So it's not exactly DC, we don't have to go into that here, but the point here being I've simulated this again as one oscillation. So again, I simulated this. I know what I put into the black time series here. There is one rhythmic component at 10 hertz. And the rest of it is just, not technically speaking, white noise. It's what's called pink noise. All that means is it has a different pattern of power across frequencies, but by definition is non-rhythmic. We okay with that? Right? So I have created this time series where there is one oscillation in it. Where do we think that lands in this power spectrum?
Presumably the spike?
Yeah. So that's sort of the basic premise here, right? If you have a true oscillation, meaning there's frequency-specific power, meaning there's something actually going up and down at that rhythm of interest, when you go the power spectrum, you see a spike or a peak of frequency-specific power. And that you can basically say, okay, this is evidence that there's power in this frequency band that is specific to this frequency, that is oscillatory, is rhythmic, and is not explained by the general character across the rest of the power spectrum. And then sort of the converse of that is if you're looking at the green band or the yellow band, there's no particular peak. And so we can then start to argue that the power in this particular frequency range is best explained by a non-rhythmic process, because we think that this kind of data contains rhythmic quality and non-rhythmic quality. And we would like to be very clean and clear about separating the two.
What about troughs? So in the pink band, there's a dip. Is that representative of anything, or is it just like non-rhythmic as well?
Yeah, so in a second we're gonna like model this and say what does it look like to try to measure these things, and you could in principle have less power than expected given your model. That doesn't actually really happen in real data. We can come back to that of thoughts on why. Here you might see that it's not actually a super clean straight line. This is just like the estimation noise basically.
So at different points of like, if you were to take a screenshot of this graph as it's ongoing, some of them sometimes look like they do have peaks. So what period of time do you have to capture data for in order to actually determine if it's like a stable finding?
Yeah, that's a really good question. And there could be lots of different answers. So I'm gonna say, let's come back to that because I'm gonna introduce the sort of the modeling framework, the methodological framework that we use to try to address, this is the problem statement. And then if we want to, we can talk about the nuances of actually model verification, because you can imagine it's not that hard to either miss peaks or add extra peaks and then still end up with potentially the wrong interpretation, right? The other thing I didn't say super explicitly up front, but I'll say now because it's latently there, I do a lot of work with simulations, and that is different from your average cognitive neuroscientist who sits with EEG data. The problem if you only have real data is you don't know what the right answer is. And that's really annoying. Unfortunately, that's how we do science, but most of the time I avoid that problem by simulating my own data so I can say, what is the answer I want to know? That is obviously not going to solve memory for us. I use that for developing methods. Because if I say my method can extract an oscillation of interest, I can simulate a very large number of these instances across lots of different parameters, like noise level, like number of trials, any number of parameters you might think about, and actually give you a sort of report card for how well the method does. So we can talk a little bit of that after we do the methodological framework. But does this sort of make sense? I know I'm going a bit like in the weeds here of signal processing, but it's the kind of like, if you don't have to care too much about the FFT, the Fourier transform, the point is there are features that we might want to extract, for example, rhythmic features, and it's actually non-trivial to figure out how to extract them. And that's going to be true of every method that is non-trivial to extract features, although the details of what the complexities are is going to vary, right? Make sense? Okay. So to sort of restate that and sort of summarize, neural field data that might look a bit like this has multiple features. And here I'm talking about ongoing recordings. You can do this with events of interest, but we're just talking a bit more broadly. So you can think about this just being resting state data, for example, or sleep data or whatever. And it has a couple different features. In green, I've highlighted a segment of data that is oscillatory. So does everybody sort of see that we can see a rhythmic character to this part? Yeah, so I put that there, it's true. But it's not always true. And so if we keep recording through time, here, again, I simulated this by definition, this has no rhythmic character to it, right? And so when we cache that on the power spectrum, and here I'm sort of like using a bit more data, it's a little bit smoother, a little bit cleaner, we can see something like this. And as I sort of introduced, but just to sort of formalize, frequency-specific activity shows up in the power spectrum as a peak of activity, of frequency-specific activity, and that almost becomes like the definition of an oscillation, meaning it has to have power at a particular frequency for it to actually be repeating. If it doesn't have power at any particular frequency, it's just random. That's still interesting maybe, but it's a different kind of thing, right? And that's what we mean by this sort of blue component, right? So this is the power spectrum of this segment of data. Now, not only am I sort of motivating, we want to be able to figure out where this peak is, or if it's there might just not be a peak. And we would like to say there are segments of data that are best explained as non-rhythmic, or that's where I'm going to use the word aperiodic. Periodic has periodicity, aperiodic without periodicity. Cool?
I have a question. So I assume the graph B is focused on the oscillatory. Yep. So graph B is focused on the oscillation that happens repeatedly in the same frequency.
Mm-hmm.
Do you have the ability to model or to find in those graphs rates of change in signal bands? So for example, it goes from 5 hertz to 7 hertz to 9 hertz in a regular manner. Would that also be able to be modeled?
Yeah.
Okay.
Short answer, yes. We can talk. So this modeling framework, as I'm going to introduce right now, is not time resolved because a power spectrum is a representation of a range of time, right? So this is the summary of, like, let's call it this whole section. And so by itself, a single power spectrum has no time definition. But as we can sort of see here, the obvious way to look across windows is to look across power spectra, right? So part of the newer components of this modeling framework are time-resolved analyses. All that really means is doing what we're about to do across windows. And we can track change and so on. Yeah.
So the whole thing here is neurons are sending signals to each other. Action potentials are constant in how big they are. So the only thing you can really change is how many of them you're doing in like a given time period. And when you have these repeating patterns and action potentials, it means that there's like a stable kind of activity going on within the neurons. Yep. And that means that they're probably agreeing on something or working together, hypothetically. Mm-hmm. Whereas when you see these more random oscillations, these things that aren't constant over these time periods, it means that the brain isn't working together, hypothetically, or agreeing with itself as much. And the kind of contrast between these two possible outcomes is interesting, basically.
Yeah, I would say descriptively that's absolutely true. The layers that could be debated a little bit are the putative interpretations. So yes, it's definitely true that in this situation, and I'm going to do a little bit of sort of like the underlying activity in a second, and hopefully that'll help. This is, let's call it structured or correlated in a sense, right? And we do think that's informative because if a series of neurons are correlated in their action across time, we have a lot of ideas of what that might mean for like the functional organization of brain activity and how that relates to the thing that the brain is doing, right? So the thing that might not be obvious to you is this has 100 years of extensive research saying how does this feature relate to cognition A or clinical disorder B. The point that I often am trying to emphasize in some of my work is this is not only present, which we knew about, but it's dynamic and interesting in a way that I think has been sometimes underappreciated. So I don't really agree that this is null or uninteresting or it's not structured in the same way, but I think we would like to argue that this might be informative physiologically as well in a different way.
I think it's probably the most interesting part.
Yeah, and again, to come back to my original premise, what I'm really trying to hammer out here is, you know, at the feature extraction point, it's sort of like something. The next thing to do is how does this relate to cognition / clinical behavior, and what does that mean? But before we even get there, let's just make sure that this is well described as this, and this is well described as this, and they're not intermixed, right? And so what that looks like is basically this. I would like to know if there's a peak as highlighted in green and where the blue line is and separate those two components. It's a very simple proposal. There's nothing super new about the proposal. If you're not super familiar with this world of work, hopefully it would actually be sort of good news if this seems reasonably obvious. For various reasons that we can talk about, this hasn't been the status quo. And what was the status quo was this. Now, this set of features is a very different definition of your data. It's descriptively fine, right? You can say there's this number of this frequency range. That's technically not inaccurate. But if you say this number represents oscillations, that's where I'm like, actually, that's not very well motivated, right? And you could redescribe your data like this, right? And to make that a little bit more, okay. Does that make sense? Okay, so that is the premise. Why do I think you should do it like this and not some other way? It's basically because here I've taken away the noise and made it very simple. You have group A, group B, you know, case control, young people, old people, people with ADHD, people without ADHD, people who did a memory task, people who didn't, whatever your groups are. And you say, oh, there's a change in the amount of power between 8 and 12, which is the alpha range, very commonly discussed. And if you record that, you might think that this happened. And if this did happen, then you could argue in the framework that I'm trying to introduce here that there was a change in oscillatory power. And you can truly say the amount of rhythmic activity changed. The orange group had less structured activity. If that was a clinical group, you might have a whole discussion section talking about how this brain is less correlated across time. And if that was something like ADHD, you might be like, oh, this brain is a little bit less sort of connected to the sort of like coordinated activity of the world around it, right? You could write about that. And that would be okay if you're living in this place. The problem is if all you measured is the power in the blue range, then all this stuff could have happened. And this is numerically exact. The numerical difference in the blue range is exactly the same for each of these 4 cases. But I would argue in terms of taking that extracted feature and saying something about it, these are 4 different statements about the brain. This is a reduction in oscillatory power. This is a change in oscillatory frequency. So these are both about the peak. And then we talk about that, what was before that blue line, that line across all frequencies, that line can go up, down, or move around. Now, if this happened and you said, oh, this is a change in alpha power, you would actually be wrong. The alpha power is the same, but because other things changed, it just sort of looks like that. Does that make sense? Now, in terms of like one of the short versions of why were people not always sort of parameterizing these peaks like this, Basically, we didn't really recognize to the extent that this was happening. We thought that background blue line was always about the same. If that was true, this would be fine. And this is a bit of a less problem. But it turns out that we argue and show, and other people have done so, this happens quite a lot. And so if this is happening, then by measuring the blue range specifically, you can't know you live in this world. You might live in this world. And then your whole interpretation is different. Does that make sense?
Would it be okay to give a quick, because you kind of explained how the applied interpretation would go of graph A. Would you explain maybe how you would interpret C or D as changes in that example of the ADHD group?
Yes. Let me see. Yeah. Sorry to keep deferring your questions, but I'll come back to that in a couple minutes. Yeah.
Awesome.
Okay, so that was all problem statement, and I realize I took a while there, but hopefully, does that make sense? Are we sort of living in a shared understanding here?
We did roughly say 3 till 4. We haven't run booked until 5, and I think most people will leave.
Oh, sorry, I didn't realize what time it is. Yeah.
No,
So
it's what I'm just saying is, yeah. Oh, so we have it booked in like 2 till 5, so we're
Yeah.
fine for time.
So I'm going to do whatever 5-10 minutes that sort of closes this particular piece. I'm going to stick around and keep talking about whatever people want to. If you do have to leave at 3, you do you. Cool? Okay. So that problem statement is what we spend a lot of time in my early PhD sort of thinking about how do we address it. And then I've sort of more or less given you the solution space. But then if you actually want to do method development, that's the word. If you want to do method development, you actually have to take this sort of like conceptual idea and cash it out in a descriptive, like mathematical or engineering sense, right? So I'll do a brief run through of that, and then we'll talk about various interpretations and applications that we can sort of explore a little bit from there, right? So what we would like to propose in this periodic and aperiodic model, as opposed to what was previously being done in like a band-by-band approach, is that the neural power spectrum can be described as a combination of an aperiodic component, so that's that line across all frequencies, which is by definition non-periodic. Anything with sort of a pattern of power across all frequencies has no specific frequency, has no frequency characteristic. But there are periodic activity, right? There can be an alpha oscillation, right? So this is our conceptual model of the data. And this is how we're going to go about thinking about the features. And then we're going to use this conceptual model, write it down in math, so that we can actually extract the features in a mathematically principled sense, right? So to do that, we have to take our conceptual model and write it down so we can sort of formalize and sort of like pseudocode a neural power spectrum. We want to define some aperiodic function. We want to define a peak function. We also actually are going to acknowledge that there could be more than one peak. And so we want to have a way to take this and measure it, model it in the true sense with these functions, allowing for flexibility that there could be multiple of these, right? And if we, again, just sort of like keep getting closer to the mathematics, you don't actually have to care too much what these numbers are, but we can take the neural power spectrum. They're all functions of frequency. They exist across frequencies. We can write down, this is a long way of saying a 1 over f function. It just means that blue line. For our purposes, it doesn't really matter, right? It's 1 over f because you have 1 over f to the exponent value. That describes the steepness of that decay. This is a very common, useful, interesting function in physics and mathematics, so there's a lot of connection points we can make. We don't have to go into them here. But if I talk about the aperiodic exponent, it is this value, which basically is that rotation. If you want to do the up-down, you get it from the b, and we're going to ignore the k. This, you might recognize, is just a Gaussian. So you've done statistics or some other place where you've heard of a Gaussian. This is a Gaussian in the literal same sense. The useful thing we can do about it is as a function of frequency, where we can put it at a particular frequency center point, a particular frequency width, and a particular frequency height.
Gaussian being like a normal curve.
A normal curve, yeah. And we get this. So now our gray line, black line, the original data, can be parameterized with this blue line and these green peaks. But this blue line and these green peaks now are not just a conceptual model, they're mathematically measured. So I can tell you the peak is at 10.10 hertz. It has a power of 0.8 power units, a bandwidth of 2.46 hertz. And that peak was detected and sits on top of this blue line which has an exponent of 1.8 and an offset of 0.05. Now, if you want to say group A versus group B, did the alpha power change? You can do so on these peak parameters where you've pre-checked whether the peak is there, and not a frequency range where you don't really know. Make sense? Oh, yeah, sorry. I use various versions of these slides, and I don't know which slide is coming next. So, yeah. That's basically like the sort of like the foundational premise. So I can talk a little bit more about code development and/or applications and/or interpretations.
Applications.
Applications. Okay. Perfect. So a couple of paired applications. In the simple case here where these are not event related, not task related, it's actually going to be aging and then clinical components. So in healthy aging, there's consistently observed change in aprotic components. And just to give you like a very, very brief overview of one of a couple papers that I've done on this topic, if you apply that model and parameterize out these components, what you get is young versus old have a very different steepness of these kind of things. And if we put those exponent values, so the steepness of these slopes across age, we get a very systematic change in age. Now, in some sense, we knew this, but a lot of prior work had done that band by band thing. And so their results for a long time was like, delta goes down, gamma goes up. This goes down, this goes up. They were describing two different changes or more than two different changes. And they were just talking about changes in oscillations. And what me and many others have shown now is actually this seems to be a change of these arrhythmic parameters. And you don't really have to talk about rhythm at all. And as we'll talk about briefly for interpretations, that really changes how you think about what this means physiologically, right? And this has been well replicated. There's like 40, 50 studies that have looked at this in this kind of way now. And we're pretty confident that one of the main things that happens in EEG, this happens to be intracranial, but intracranial or extracranial EEG, is the aprotic component of the data shifts across age. Good to know, changes our interpretation. It also gives us a new baseline for thinking about Alzheimer's. A lot of previous work in Alzheimer's has talked about change in the alpha range, and also separately in some of these other band ranges, right? And so now we've said, okay, what we used to think were band particular rates changes in aging, we now think is aperiodic in healthy aging. In non-healthy aging, in a particular clinical case that's related to age, what is going on? And so we did a reanalysis where we took control and people with Alzheimer's. So two groups, again, the sort of like hypothetical study that we've been talking about. And actually, if you do the same parameterization approach and you put them on top of each other, age matched, there's no difference in the aprotic component. But there is a difference when you isolate the periodic component, right? So again, if you wanted to build a prediction algorithm for Alzheimer's versus not, you could just take the power at this frequency, probably predict pretty well. People actually do this, and it's sort of fine. But if you want to say, what do we think is changing physiologically, you want to know if a change in any particular frequency is coming from this component or this component. And so this, through this work and other work, we're able to argue and show and demonstrate that we really think healthy aging is a shift in this component of the physiology, but unhealthy aging in the case of dementia, Alzheimer's dementia at least, is a change in this component, right? Now again, coming back to your sort of point, I think, about this is a case where Alzheimer's patients have much less structured activity. So this sort of, we can speculate into the functional role here because we've been clean and clear about the feature extraction. People with Alzheimer's have a much less correlated neural activity over time. This kind of correlated neural activity over time is known to relate to things like memory performance and so on. And so we can speculate that this sort of like fuzziness in the ongoing brain activity where it's less consistent, less keeping on sort of the rhythm of the beat, so to speak, is maybe related to those symptoms. And this seems to be the case where actually this change in power at a particular frequency band is something that does predict not only disease diagnosis label, but also relates to certain kinds of symptom scores and so on. And then in non-clinical work, we have work that shows that these different features relate to different ways to things like memory. So we can try to tie that all together. Does that make sense? So those are a couple of the simple applications. Questions, comments, concerns? Okay. Do you want a minute on modeling and underlying feature generation? Cool. All right. We talked a little bit about why we might be interested in rhythmic activity, because it's a kind of structured patterning of neural activity that we think the brain is engaging with. And there's a whole world of research that it might be part of two things. One of which is lining up the activity of the brain structurally and sort of strategically with relationship to the world. Now, not everything in the world is rhythmic, of course. In fact, most things in the world are not that rhythmic. But rhythm can be, there can be some variation here. So some people have shown, for example, that these sort of fluctuations seem to line up with sampling pieces of visual information of interest, and that there seems to be a strategic way that alpha relates to visual processing. Other people have shown that in the lower frequencies like delta theta, it seems to line up with word generation. So language is not rhythmic, but it's sort of pseudo-rhythmic, right? Most languages have a pretty similar syllable rate on average. And it seems like, to some extent at least, these brain oscillations line up with things in the world. So that might be a strategic way to deploy neural activity to the things around us that we care about. You might have heard of like rhythmic pattern generators in sort of motor cortex and or spinal cord. This is sort of in the same world. The other thing we think it might do is if you have lots of different brain regions with, what do we have, 100 billion, 100, some crazy billion number of neurons, if you want to strategically connect and disconnect different regions in sort of like a functional connectivity sense, which I think is maybe what Dario was talking a little bit about that. One way we think of that is if you have two parts of the brain rhythmically in phase, and let's say the top of the peak is when you do stuff and the bottom of the peak is when you shut up, then these two parts of the brain like this can talk to each other. It's like being on the same telephone wire. If they're doing this, they can be strategically out of sync. And if you start thinking about that instead of two regions but n regions, you can then start flexibly manipulating which parts of the brain are connected to each other. So that's where we have 100 years of literature on why these rhythmic components might be interesting. And to be clear, I do think rhythmic components are really interesting, even though a lot of my work is slightly like undermining them in some ways. I would argue we want to just be more, we need to be confident when they're there so we can be sort of appropriate about these interpretations and specific about those interpretations. We don't want to make that interpretation if it's not true. Now, the other point that I've sort of alluded to but haven't really demonstrated is to say that this aperiodic component of the activity, that it is neural, that it is physiologically interesting, and then we can robustly measure it, coming back to the initial goals of the thing, right? I've just told you it's there. I haven't really said anything about it yet, right? Why do we think it's there, and why do we think that might be interesting? To that, we go to some modeling done with a lab mate in my PhD work. If we think of the very basic premise of what happens when we record electrical activity from the brain, we have a bunch of neurons. And here I'm putting an electrode inside near the neurons. That electrode could be far away. It's sort of the same principle, right? So we have neurons, and different neurons do different things. And we're aware of what neurotransmitters are. We're aware of excitatory versus inhibitory neurotransmitters. GABA and AMPA are words that we are familiar with, right? So if you're an excitatory neurotransmitter, you create a postsynaptic potential on your next neuron in one direction. That is an excitable direction. And if you're an inhibitory neurotransmitter, you do the same sort of idea in the other direction. Does that make sense? Okay. We talked a little bit about what we're recording. It's not actually neurons spiking in the action potential sense. For various technical reasons, they're very sharp and brief. That is hard to measure. But postsynaptic potentials are actually, there's a lot of them, and they can be correlated, and they're relatively slow for brain speak. And they can sum up. And so what we actually think is happening when we record an LFP or an EEG is that these features come in. Each time this neuron spikes, it lets out a postsynaptic potential here. And if it's excitatory, it goes in this direction, and it's short and steep. And if it's inhibitory, it goes in the opposite direction, and it's a bit longer and slower. Now, again, the details don't matter too much, but for our purposes, these are exponential rise and exponential decays. We can write down the formulas for what those look like. We can then sum a bunch of them together over time. And this gives us our basic, very, very basic model of EEG is summed activity of postsynaptic potentials, some excitatory, some inhibitory. They get summed together. What does that give you? It gives you a 1/f curve. So we actually argue that before anything else, you should expect this to be a neural part of your data. It's, it could have sources that are non-neural, that are muscle or whatever. And sometimes these have correlated structure and they're rhythmic, but beyond that, they're just there like this, and there's an aperiodic component to your data. Why does it change? Well, actually, it turns out you can just move around how much red versus how much blue, and that's going to move around. Because you sum the black line from the orange plus the blue, the black line moves around as you change that. So the aperiodic exponent is not only predicted by this basic postsynaptic potential sort of basic modeling approach, but it suggests that as that black line shifts, as it rotates, as that exponent value changes, it's a change in how much excitation and inhibition is happening. Now, excitation and inhibition is one of our basic principles we talk about brain function, right? If you're asleep, you have a particular pattern of excitation and inhibition, which is shutting certain things off, and we can actually see in sleep, you have a very different aperiodic component than if you're awake. And at a shorter time, if you do task-related analyses, when we give you a memory object, you often have a very rapid shift of this aperiodic character that might be sort of the local, temporally resolved processing. So somebody asked about time resolved processing, I can show you in a second, but basically if we do this through time, we see this black line move around, and if there's a change in these parameters, it could be like, let's say, a burst of excitation, a burst of inhibition. Does that make sense? Okay, so that was the sort of short version of interpretations. I'll do a short version of code pragmatics, and then we can discuss as wanted, right? So to sort of like behind the scenes, how do I do all this work? As I sort of told you, it's all Python development. But as you maybe got a sense of, one thing that my research connects to is trying to develop methods to talk to a bunch of empirical researchers who are not mathematicians and are not engineers. And neither am I, but I have spent a lot of time trying to figure this out, right? And so for both science communication reasons and for other sort of like broader open science reasons, we try to do open source projects. And what that means to us is that, again, a lot of the time there's no real data, so it's easy for simulations, but all the code is not only available, but actually like practically interpretable. And I'll show you what that looks like in a more literal sense. But a lot of the things that I've shown you are built out of these little simulations and little demonstrations, and we do actually do the same thing for empirical analyses. All the code is available, the data is available when possible. And we do things like trying to sketch out all these different quirks that can happen. If you do want to look at oscillations, I've told you like one main big thing that can go wrong. In this paper, we talk about 7 different ways you can screw it up if you're not like really clean and careful about that, right? I didn't go into the details, but there's a lot of, you can imagine there's a lot of ways you can measure aperiodic activity, and we do a big methodological sort of comparison exploration. And again, these are all openly available, where we have implementations of the methods and demonstrations of how they work and how they relate to each other. We talked briefly about ERPs. One thing that I'm always trying to do in my work is I want to know not necessarily, sometimes what a particular paper says, but more what is a pattern of analysis that people are doing. And so I would like to say, what is the average approach of 1,000 papers as opposed to what is this paper doing specifically? And you might think about doing that slightly differently now, but 10 years ago, what we did is we built text analysis tools to automatically search, find, download, and then text map what papers are doing. So when I tell you that roughly 1,000 papers do this kind of thing, that's data-driven. In a sort of interpretable way, not just, I think this is the case. These are projects. You guys know what GitHub is? They're all on GitHub, right? The other version of that is that all these tools are open source available. So the thing that I've been introducing and motivating and showing you and using is called spectral parameterization. It used to be called FOOF, for fitting oscillations 1/f. Spectral parameterization is the new version. It doesn't, the differences don't matter. It's basically fitting this model to the power spectrum. It is an open source, documented, robustly developed Python module. What that means is if you've done code development, it is version controlled. It is semantic version controlled both in tracking, but also semantically versioned. So if there's a new version of it, I tell you what changed and why, and you can track if you want to update to that. It is available on GitHub, and it has a huge documentation site, I'll show you that in a minute, where actually there's a lot of support that if you want to do this, and you're not an engineer, but you do have an EEG data, and you have Alzheimer's data and non-Alzheimer's data, and you used to press a button and get band by band, you can now do a little bit of work to hopefully motivate and understand how this works, and then apply this in as clean and clear as a way as possible. Behind the scenes, a lot of our simulations live in a different place over here, and our text mining lives in a different place over here. These are all openly available if you're on Python. If you're using Python already and you do pip install specparam, neurodisp, Lisk, you'll get all these things. And yeah, somebody asked about R before. I use Python because it is the most general purpose open source language that is in high use for this application. Signal processing is a little bit further developed in Python than in R. I do use R for statistics. R is fantastic for lots of different pieces. It's just not as developed and not as common for signal processing. So Python was the right place to live. Some people use MATLAB. I don't use closed source tools. Best of luck to the people who do. Okay, so to briefly, nope, that's not right. So when I talk about these sort of like openly available projects, if you start, one of the reasons that Python I think is very useful is it being general purpose. You can do sort of like full range development. You can do data management, data analysis, but you can also do like web design, not like JavaScript web design, but you can basically do a lot of things that basically get your Python code piped out to a website that other people can look at. So if you want to, again, as I mentioned, a lot of our work here is basically science communication to a large potential user base of people who are psychologists, trained in cognitive science, using these kind of signals. We're never trained in engineering, and we're trying to step them through how does this work and how do we analyze these signals appropriately without just giving them a math textbook. I don't think that really helps most of them, right? So we sit down and go through things like, what does it look like to have different kinds of signals? What does it look like to apply different kinds of transformations? So I've been using some of these. What does it mean to do time domain? Data transforms, so convolution, which is really what we're doing when we're doing filtering. A lot of the other ways, like I didn't talk about time domain stuff. You can do a lot of stuff in the time domain that also can go wrong because time domain is also complicated and so on. Then we build things like this, where that project I alluded to of all the different things you might want to think about if you do feature extraction for oscillatory features. It has a paper in the traditional sense that you can download, you can read. But to me, that's not the real work of the project. The real work is not only the open source code repository, but is also sometimes a little bit opaque. But we can then turn that into, so if here we're using Jupyter Notebooks, there's tools that if you have a Jupyter Notebook, you can automatically turn it into a website. And then we do that. So if I want to say, what is the important point of evaluating oscillatory presence? Is there an oscillation there at all? This is a rendered website that actually shows you all the code that makes all the figures and all the pieces. So if you have a time series with a series of zeros and a single one, that has a power spectrum with non-zero power. And to me, that's like the core of the problem. There's no question that this is oscillatory. It's just clearly not oscillatory. But it has power in every frequency. So power in a frequency cannot possibly mean something is oscillatory, right? So we start from the very base cases, build them up, and then these create all the pieces that go into the paper. So if you want to see how any single thing was done, it's all available there. So these are the projects that are alluded to. And then when we talk about the tooling, again, we talk about open source on GitHub. So this is the source code. Sorry, it's slow. But it has lots of tutorials that are also built in code in a similar way. And so you can see not only sort of like the motivating factors, but the code that does the thing. and then things like visualizers that we're trying to show you different pieces of this. And if you want to just look, how does this model fitting actually work? I didn't tell you how the model was fit. It's not super important for our purposes here, but if you ever want to look into it, you can say, okay, there's a base model object, and it is just some openly available Python code that you can look at. And of course, some people will look at the code, but typically we are doing this so that you have, if you have well-developed code, you can automatically create these kind of websites where you can interrogate the documentation for a particular sort of computational element here. So this model object, it works a little bit like an R model object, like it's the same premise of fitting your data. It's literally model fitting. And it follows some of those same sort of standards, but all the code is described and so on. So that was a very brief version of the applications, the interpretations, and the behind-the-scenes code development. Again, to sort of try to zoom out slightly, we did a bit of a rabbit hole on some of the specifics of neural oscillations and EEG data. Maybe you'll do EEG, maybe you'll remember this, great. Maybe you'll never get anywhere near there. Hopefully it wasn't too boring, but hopefully there's some sort of, if you take one thing, it's that for some purposes, for cognitive neuroscience, for clinical neuroscience, where the goal is understanding, feature extraction from any kind of neural recording is extremely important and often under-examined, I think. And if you're getting started in a research project, I do think it's worth the time to set yourself up in a practical sense to be using things like open source code, but also to really think through that processing pipeline. We're often just sort of given processing pipelines and said, this is how we get X feature. Of course, we can't always interrogate every component of science, but sometimes we should interrogate at least some of them. And if you dig around the literature, I spent a lot of time figuring out what people are doing in the literature. The problems with these kind of situations are often, if not super explicit, latent, right? One of the reasons we wanted to address neural oscillations is for all of the really interesting and powerful work, there's a lot of inconsistency. Study A doing supposedly the same thing as study B, but they both find different things. And if you start like logicking through the things that could be happening, it might be because we're not very specific in the features that we're extracting, right? So if you see this kind of inconsistency across the literature, you really want to sit down and think about pipeline management, feature extraction, and feature interpretation, right? So hopefully this case study, if nothing else, motivates that sort of component. I do have a bit more time. You can ask for anything else we go through as a group. We can do a bit more discussion. We can have questions. It's, choose your own adventure. If people want to go, you should also do that.
Sorry, can I just ask?
Yeah, of course.
You said a lot of your work revolves around simulating the initial data,
Mm-hmm.
so you know exactly what's going into the system.